Bismillahirrahmanirrahim. In today's interaction, we will discuss the CAM design using polynomials, and I will summarize the journal thumb rules and tips. Before attending this video lecture, you must know that what are polynomials, what is the degree and order of polynomial, what is SVAG diagram which is used for CAM design. And after successfully attending this interaction, you will be able to know that what are the polynomial types used for double dual CAM follower mechanism. You will also know what are the different polynomial types for symmetric single dual CAM design, CAM follower mechanism. You will also know what are the polynomials for asymmetrical single dual CAM follower mechanism. CAM design, you know that a polynomial function is something like this, where the higher exponential power of independent variable x will be known as its degree, and the number of terms involved will be its order. So if we are going to define our CAM design with a polynomial, this is the displacement function for polynomial, where independent variable x will be replaced by theta by beta. Beta is the duration of the segment and theta is the varying angle at any instance within this beta. We can also replace this theta by beta by time if we are defining our independent axis with time. And S stands for follower displacement. Before going to the further details of dual-based CAM follower mechanism, remember that the boundary conditions for any CAM follower mechanism for dual are quite simple and known. The figure shown is the rise segment of a double dual CAM follower mechanism. And these horizontal lines in displacement, velocity, and acceleration curve are of 12. Remember that the displacement at 12 will be taken as constant. So if it is lower 12 or the follower is at the lowest height, we will call it zero displacement. So this case is displacement 0. And if the follower has taken some height, we will call it the rise displacement or h displacement, where h is the maximum height gained by the follower. In a rise fall dual mechanism where there is only single dual, so this displacement will be 0 at both ends, or it will be h at both ends. So the dual mechanism for single dual CAM follower mechanism will be having the same displacement for both ends. If we look into the velocity of dual, at the start and end of the segment of this moving velocity segment, the velocity of dual will always be 0. So whenever some segment is connected to dual, its connected velocity will be 0. The next boundary condition is acceleration. So acceleration is also 0 when there is dual. So whether it is end of dual here or start of dual here. Because at dual, the follower is not moving, so velocity and acceleration will be obviously 0. The jerk can be discontinuous if we control the CAM till here, because the fundamental law of CAM design asks us to keep the acceleration 0. If you want to further control the jerk will again be taken as 0, and for any dual, whether it is start of dual or end of dual, the jerk will be 0. But most of the time it is not necessary until the jerk is causing some design problems or functionality problems. And also when you include the jerk, the degree and order of the function used will be increased, and this will this will decrease the control of the control over the polynomial. And the curves between these segments, these dual segments, will be having more inflection points, and maxima minima problem will be involved when we will be taking the derivatives or displacement for velocity, acceleration, and jerk. So after understanding the boundary conditions of dual, we move further. So if you have the critical extreme position design in front of you, you must decide that what is your CAM follower mechanism type, whether it is double dual or single dual. So these are the 6 dual segments for a double dual CAM mechanism. If, for example, if we have a double dual CAM mechanism, we have to further see that whether we have to control this double dual mechanism till acceleration. If we have to control it till acceleration, then we will be having 6 boundary conditions as shown in the figure, because there will be 3 duals on the right side and three duals on the right side and 3 duals on the left side. So there will be 6 boundary conditions. Based on the boundary conditions, you can solve 6 coefficients. When you can solve 6 coefficients of boundary or coefficients of the polynomial, the order of the polynomial will be 6, and degree of polynomial is always 1 less than the boundary condition, so that would be 5. So highest power of theta by beta solved will be 5. But it doesn't mean that there will be all coefficients available here. When you will solve it, you will know that 0, 1, 2 coefficients will become 0 if we consider the example shown here. And we will call this resulting polynomial as 3, 4, 5, because the exponents, the powers 3, 4, and 5 for the independent variable will be there because it has non-zero coefficients. So for any example, a single example, you can see this will be the displacement function. And if we have to find the velocity, we'll take its derivative with 1 by beta additional given out. And for acceleration, we will take another derivative, and for jerk, we will take another derivative. But if we are not controlling it to jerk, we can plot it as discontinuous, but there it will not be 0 at the valves. So the resulting equation, for example, will be something like that. The resulting figure or plot. So this is a typical example of double dual cam follower mechanism when you have the control till acceleration. Now, if you say that I don't want to keep the control till acceleration, I want to further control it till jerk, then you will be having 2 more additional boundary conditions. So it will give you 8 boundary conditions in total, 4 for the right duals, left duals, and 4 for the right duals. So it will make 8 boundary conditions in total. 8 boundary conditions means a polynomial of order 8 and degree 7. As I told, the degree will be 1 less than the number of boundary conditions. So you will insert these boundary conditions into the journal polynomial functions for displacement, velocity, acceleration, and jerk, and you will find the values of 8 unknown coefficients. If I take an example, for my example, I found that 0, 1, 2, 3 coefficients were 0, and I was only able to find the coefficients for 4, 5, 6, 7. And for this, based on this polynomial, the typical example shown here has a displacement polynomial shown something like that, and if you plot it, it will be something like that. So here, if you see, as compared to the last one, the jerk is also controlled at the boundaries, but this has increased the highest power of polynomial, and that means that there will be more waviness, more or less control between these extreme positions. So that would cause some fluctuation of forces and motions, which can be a problem for specific types of CAM follower mechanisms. So we try to avoid this jerk in most of the cases until unless it is a requirement of the design. So let's move to the next portion, which is single dwell. So if you have decided that your mechanism is not double dwell, rather it is a single dwell cam follower mechanism, then you will have only single straight lines for position, velocity, acceleration, and jerk. And if you want to further design it, the further option is that whether your single dwell is symmetrical for rise and fall, because other than dwell there will be a rise and a fall. If the rise and fall segment are of equal duration, that would be known as symmetrical rise and fall. So the good option is to keep the whole cam profile into two segments only. One segment will be the dwell and the other will be drawn here for the connected or combined rise and fall. So if I see the conditions here and I don't control the jerk, the boundary conditions will be 6 based on these three ends E on each side of the dwells. And there will be additional boundary condition for the value of rise present at the quite middle of this rise and fall segment. Sorry, it will be drawn here on the left. I will show in some minutes. So there will be a rise or fall just in the middle portion of this additional rise and fall segment. So that would be the seventh boundary condition. So these 7 boundary conditions will result in a polynomial of order 7 and it will be having a degree of 6. So if you find the coefficients of those polynomials, 0, 1, 2 coefficients will be 0 and you will be able to find 3, 4, 5, 6 polynomials. So that's why it's called 3, 4, 5, 6 polynomial. And its displacement polynomial will look like something like this for a typical example I've considered. And if I plot this typical example, this will be something like that. So you see the displacement is 0 and 0 in the beginning and end because of the dwell boundary condition. Velocity is 0 and end. Acceleration is 0 and 0 following the cam follower mechanism, and jerk has discontinuity here because we didn't control it. And if you see, we have very high accelerations here. So two segments are giving some good options to us, but also there are some high accelerations involved. If you see that your single dwell is symmetrical rise and fall, but now you say no, if it is in case not symmetrical and it is asymmetrical rise and fall, then you have to go for 3 segments. And I also say that if even in case of symmetrical rise and fall, if you want to control further on any values of velocity, acceleration or jerk, you can involve additional boundary conditions, but it will increase the order and degree of the polynomial. So if in this case you think that your design requirements are not symmetrical and the rise and fall are of different duration, then the rise will not be completely in the middle of the combined segment. So you are not able to do the same thing by 2 segments, because if you will do it, you will see some abnormal behavior within the segment. So in order to avoid that abnormal behavior, the best approach is to again design the mechanism into 3 segments. So one will be rise, then there will be fall, and then there will be dwell. Or it can be anything where dwell will be on one side of rise and fall. So rise and fall must be connected at some end. The next key thumb rule here is, if you are going for 3 segments, within the segments which are not dwell, non-dwell mechanism segments, you have to select the segment which is larger in duration. And larger in duration segment uh, will have smaller acceleration because the cam follower will have more time to reach its extreme position. So it will take more time and the acceleration will be smaller. So that would result in a smoother and low force requiring cam follower mechanism. So for example, if I consider an example where the fall is the larger segment, so we will start with the fall. segment, and if you make it something similar with the single dwell, you will have 5 boundary conditions based on the requirements you have uh, in the larger form, and it will have an order of 5 and degree 4. So the polynomial you will see eventually will be 0, 2, 3, 4. So the polynomial resulting will have some value like this. I haven't plotted it here because of the lack of the space, because I have to add another segment. So when you have defined the larger rise, the fall will be connected to it. So for the smaller rise portion, you will define its own boundary conditions, and these 6 boundary conditions will have the 5 normal boundary conditions and one additional boundary condition which will be coming from the acceleration taken from the larger fall. So that was the reason we chose that as the starting segment. So this segment will give the second derivative of this will give the acceleration, and when we will put all the beta values, we will get the acceleration, and we will take that acceleration as an additional boundary condition for the rise. So it will have 6 boundary conditions, and based on these 6 boundary conditions, the order of the polynomial will be 6 and the degree will be 5. So if I draw this 3, 4, 5 polynomial, it will have this equation. This is taken as a typical example. The coefficients can vary from design to design, from a problem to problem. Also, the h will be different based on the height or rise required in that cam follower mechanism. And the coefficient 0, 1, 2 will be 0. So that's why that would be known as 3, 4, 5 polynomial. So this single dwell asymmetrical rise and fall will use 2 polynomials, one 0, 2, 3, 4 and the other 3, 4, 5. So based on all this discussion, let's define some thumb rules for when you are designing a cam follower mechanism, and these are very important. So the first thumb rule is, whenever you have some cam follower mechanism in front of you, start with the segment for which you have the most information. The information is maximum. That would give a good control on the requirements you have. Then secondly, when you are selecting any segment, keep the number of boundary conditions as minimum as possible. That was the reason that when we were doing the single dwell mechanism, we didn't go for jerk mechanism, because we didn't want the high order degree and polynomial, high degree and order polynomial. So when you will keep the boundary conditions lower, the degree of polynomial, the inflection points, and minima, maxima, all these will be lower. There will be less number of coefficients, and there will be more control over the polynomial function. So you will not have some haphazard values of velocities, acceleration, and jerks other than the extreme positions. So uh, also, as much as possible, keep the number of segments minimum. So if the 2 segments are possible, non-dual segments, keep them 2. If 1 is possible, keep it 1. The fifth rule is that if you keep number of segments very small, but the degree of polynomials shoot, or there is some haphazard behavior of velocity, acceleration, of jerk, which is causing severe problems for you, then you can avoid rule number 4 and you can increase the number of segments. And the last rule is that if you have neighboring non-dual segments like rise and fall connected, or fall or rise connected, there is no dual in between, you always have to start with the segment which is of longer duration. This is because the longer duration segment will have more time to reach its extreme positions, so it will have less acceleration, so it will not shoot to reach its endpoint. It will have more time and duration to reach. So less accelerations will be there. Less acceleration means less dynamic forces at the end. So these are the 6 points. Always keep these 6 points in mind when you are designing a. Based on all the video and knowledge I have given you, let's show you a problem. if you have a single dwell mechanism that has symmetrical rise and fall, so it means that it is RFD or FRD mechanism. It has only two segments. It means that rise and fall are connected into one segment and dwell is the other segment. And we want to control it till jerk, not till acceleration. So based on this situation, in your opinion, what would be the number of boundary conditions? What would be the order and degree of polynomial used? And if you solve the polynomial, what will be the value of non-zero coefficients? And on the basis of that, what is the type of polynomial you will end up with? I hope you can do it. Thank you very much for watching this video. If you have any comments or problems, do write them below, and don't forget to subscribe my channel because it would help you notified when I am uploading new videos and keep you connected with the knowledge I am gaining and delivering to others. Thank you.